matter, but what we want would matter also. I got to start teaching though, baby. All right, continue. Okay, good morning, lads and ladies. Welcome back to Calc 1. Today is another exciting day. We're going to continue talking about definite integrals. We're going to learn one of the biggest theorems in all of calculus dumb. So yeah, let's do it. I think you guys will enjoy this one because it's going to give you a route out of sigma land. So you'll be able to formally and properly compute integrals without wandering through that sigma notation stuff. That's essentially what we're looking at today, is the mechanism by which most people compute most integrals. I had to take down and put back together my my little office setup here over the last few minutes because I was working on my laptop yesterday, but I think I'll go ahead and turn on the screen share and we should be able to get this to launch. Got it all hooked up again. Totally unrelated, but if anybody has recommendations for a laptop to replace ThinkPad X230, I am open to ideas because this thing is capital D dead. Or if anybody refurbishes laptops and is interested in one of these old bad boys, I don't suppose it'd be proper for me to do commerce with you guys. But if you have recommendations, I would be happy to hear them. Okay, let's do it. This way, yeah. This is MAC2311.002. It's a lecture, and it's 328, 29. There we go, 29. 21. Oh, and I wanted to address a thing or two. I got an email. I did double check with the calc committee, and it is okay to go ahead and curve that test. I haven't applied the curve yet, so let me first. Today, we're going to learn or begin work with the fundamental theorem of calculus. There's actually two of them, theorems of calculus. So this is exciting for the reasons I mentioned earlier, right? FTC, particularly FTC2, the second one, is the tool that most people use to compute definite integrals. And it gets us out of the genuinely hard work that exists trying to do that directly from the definition. So it's a theorem that connects a couple objects. And one of the objects that it connects to another is the definite integral. It connects the definite integral to this thing, an antiderivative that we talked about last week. And that will allow us to compute the definite integrals without capital sigma stuff. And that's really all we're doing here, but let me go ahead and add in the announcement. I'll be applying the exam curves today. Last Friday, when I had all those meetings and I was able to get permission to do this, that was wonderful. It went fine, but I was just busy and I didn't get around to doing it. So I will applying the exam 2 curve, which remember was 10% today. So I had intended to do this last Friday, but it just got away from me. I was a little busy. I think everything else is pretty much on board. Yeah, not really much else to say. Some folks have been asking when exam 3 is. Exam 3 is most likely going to be in the last week of class. If for some reason I choose to push some material to be tested on the final only, we might have it the second to last week of class, but most likely exam 3 will be the last week of class. And then of course the final is on the final day. So let's get into it. I think rather than just dropping FTC on you, I would like to look at one or two kind of little examples, and I think those little examples will help you make connections on your own before we get into the statement of the theorem. And that way, when you see the theorem, rather than looking like gobbledygook, you'll recognize the pieces. So consider the following example. I might ask you to compute f of 0, and this is a capital F of 0, capital F of 1, capital F of 2, capital F of 3, and capital F of 4, where capital F of x is integral from 0 to x of, let's say, 2t dt. Functions like this can be a little bit hard to understand. And that's the reason, rather than diving right into FTC, I want to introduce it through an example. So you've actually seen some problems of this nature in your homework. Hopefully you've put a little bit of time in, and you are at least familiar with what this thing is asking, but I'll go through it very gently. That's it, that's the whole example. We might say, then guess at an algebraic representation capital F of x. Right, so we're just going to basically make a little table for capital F. And we're going to do that by computing those values in terms of this definition. And once we know the outputs corresponding to the inputs 0, 1, 2, 3, and 4, I have a feeling you will be able to tell me precisely what f of x is for any number x. Then we're going to look at that result and compare it to the definition of the function f here and see if we can't notice a connection between the algebra of this thing and the algebra of this thing. But let's do it. Let's just do it. So we'll say this is 1, 2, 3, 4. And here what I'm going to graph isn't capital F, it's little f. F of t equals 2t. Just see. How to get the values of capital F out from this. So we know what this looks like. It's a line with slope 2 and y-intercept 0. That means that over here at x equals 4, this is actually 8. I should have left some time here. I'll just put points on here. This is 4, 8. This is 3, 6. This fellow would be 2, 4. This fellow would be 1, 2. This is my t-axis. Right? So let's see, what is f, capital F of 0? That's the integral from 0 to 0 of 2t dt, right? Capital F of x is the integral from 0 up to x of 2t dt. So if I plug in x equals 0, that means I'm plugging in a 0 up here. So f of 0 is the integral from 0 to 0 of 2t dt. The integral from 0 to 0 of anything is always going to be 0. We can try to think of it as areas, right? It's the area bounded under the function f of t equals 2t. It's the area under this curve from x equals 0 to x equals 0. There's nothing there. And this is true in general. So this one, 0. And like I said, the more general rule, I can add it in over here. The integral from a to a of any function, this is always 0. Whether the variable is t or x doesn't matter. We usually see the variable x, so I'm writing the rule in terms of variable x. But yeah, the integral, definite integral from some number up to that same number is asking for an area, but the width of the region is 0. You could actually use that theorem we had from earlier last week, the capital M, little m theorem, to show that 0 is both an upper and lower bound for this integral. So it always have to be 0. This gets more fun though as we start computing f of 1, f of 2, f of 3. So let's just do that. F of 1. This would be the integral from 0 to 1 of 2t dt. So that is, if I come over here, that's this area, right? The integral from 0 to 1. So it's the area bounded by f of t equals 2t from 0 to 1. That's this little triangular region. And the reason I chose this function is because these will all be little triangular regions, so their areas will all be easy to compute. What is this area? Who can help me out? Show me you've been paying attention to the homework.
1.
I heard an answer there, but I think it got cut off. So this is a triangle, right? So the area should be 1/2 the base times the height.
It's 1.
Yeah, it's 1. It's 1. Good. So 1/2, 1 times 2. And I'll even write it like that just to help us see the pattern. 1/2 times 1 times 2. And that is indeed 1. Thank you, both Mackenzie and Trevor there. Okay, we're going to keep going. We're asked to compute f of 0 up through f of 4 for all the integers between 0 and 4. So the next one is capital F of 2, which is the integral from 0 to 2 of 2t dt. So that is skills are not that good. They don't need to be. So that is this whole triangular region, right? That's this whole thing, the area from 0 to 2. So that's this whole region. So what is that?
4.
Yeah, exactly. It's 1/2 times this base times this height. So here the base is 2 and the height is 4. So that area, 1/2 base times height, is 1/2 times 2 times 4, which is indeed 4. Capital F of 3 would be the integral from 0 to 3 of 2t dt. Would be the area of the triangle now extending out this far. So if I let the triangle march all the way out to here from 0, then the area is 1/2 times this base times this height, which is 1/2 times 3 times 6. Which is 3 times 3 is 9. All right, the 6 and the 1/2 can cancel a common factor of 2 there, and you get 3 times 3. We'll go ahead and do this last one. F of 4, capital F of 4, is the integral from 0 to 4 of 2t dt. And so that would be the area bounded underneath 2t all the way out to 4. And that's this triangular shaded area, right? So each time we add a little piece, we're integrating the whole thing. So we're going from 0 all the way out there. So this would be the area under f of t equals 2t from 0 to 4. So it's 1/2 times this base, which is 4, times this height, which is 8. So that's 1/2 times 4 times 8, which is 16. All right. So we've completed the first part. We've computed f of 0 through f of 4 for this function. The second thing we're asked to do is guess at an algebraic representation of capital F. So if f of 0 is 0, f of 1 is 1, f of 2 is 4, f of 3 is 9, and f of 4 is 16. What do we think? So it looks like capital F of x is what? What function have you seen that has these input-output pairs?
X squared.
X squared.
Right, yeah, this looks like the squaring function. X squared does that. 1 squared is 1, 2 squared is 4, 3 squared is 9, 4 squared is 16. And if you were to look at this and send it all the way out to some capital X, you would have 1/2 times x times 2x, which really is x squared. It's not at all hard to prove that this really is x squared. But I think it's easier for us to digest it if we see it little bits at a time. Okay, that was fun. But remember, we were doing this for a reason, to try and give some context to a theorem that I haven't shared with you yet. So I want you to think for just a second about the function we were integrating and the function we got out. And pretend like you have some special glasses on that make t's look like x's. What's the relationship between little f of t equals 2t and big F of x equals x squared?
If you add 1 to the exponent, then divide the coefficient by that.
It's the antiderivative?
Precisely, yeah, you're both right. If you add 1 to the exponent here, if you take 2t and you antiderive it by adding 1 to the exponent and then dividing by that new exponent, you would get t squared. Now, t squared and x squared, right? So this is an antiderivative for this, just with a different variable swapped in. So this says something. This says, at least in this case, the integral is an antiderivative. So the note I would make here is that this satisfies the definition of an antiderivative. Antiderivative in the sense that capital F primed of x is equal to little f of x, right? If you swapped in an x in little f, you replace the t for an x, what you would get is the derivative of this function. In other words, the integral here, the function defined as the integral from 0 to x of little f of t dt, turns out to be an antiderivative for little f, just with the variable swapped from t to x. The more general result here, the thing that says that this always works, that if you define big F to be the integral from anywhere up to x of little f of t dt, then big F is an antiderivative for little f, that is FTC1. All right, so I'll hold here just for a second in case anybody needs to write anything down. Are there any questions about the actual computation we did here? Any questions about how we got those numbers out? Okay. So let me now show you the theorem. This is the first part of the fundamental theorem of calculus. We call it FTC1, or fundamental theorem of calculus 1, aka FTC1. what this says is if little f, called little f of t, is continuous, then the function big F of x, defined as the integral from a up to x of little f of t dt, this function, which remember for us came out to x squared, is differentiable. And big F primed of x is equal to little f of x. This is a big deal. It tells us a few things, and I'm going to kind of go through those things, and then I'll show you how to use this in the type of problems that you'll see in this week's homework. First, why is this a big deal? What is this saying? Well, first, pay attention to the objects in question. Little f of t here is a continuous function, and big F is defined as the integral of little f. And big F is differentiable. Which one of these is a stricter condition? If you're continuous, does that mean you're differentiable?
No.
No, right? We remember that from exam 1. That was one of the, I think, the first true false question on exam 1. If you're continuous at A, then your differentiable at A is false. If you're differentiable, is it true that you're continuous?
Yes.
It is, right? So this is the stricter condition. It's harder to be differentiable than it is to be continuous. Remember, continuous means connected, and differentiable means smooth when we're talking about graphs. So these are both sort of smoothness conditions, right? A continuous function is nice in the sense that you don't have to lift your pen to draw it, but it could still have pointy edges. A differentiable function is even nicer, meaning that, yeah, you don't have to lift your pen to draw it, right? A differentiable function, it has to be continuous, you don't have to lift your pen, but also you never have to draw a jagged corner. Differentiable functions are nice and smooth. So this says that when you integrate a function that may only be continuous, you get out a function that is differentiable. So integration, and this is a very high level observation, integration is a smoothing operation. Meaning when you take a definite integral, the thing you get out, if you define a function as a definite integral, the thing you get out is smoother than the thing you put in. That's fucking fascinating. And it's not at all obvious. So integration can turn continuous functions into differentiable functions. My favorite example of this is the integral of the absolute value function. If you play this game with the absolute value function, you do get out a differentiable function. You get out x squared again, actually. X squared over 2. But that's the idea. So integration is a smoothing operation. It takes you up one level in smoothness, which is huge. It's not at all obvious, and it's a really big deal. However, it doesn't really help us with any sort of computational problems. It's just something that you should keep in the back of your brain all the way through Calc 2 and all the way through Calc 3, specifically when you get to Stokes' theorem at the end of Calc 3. Integration is a smoothing operation. What else is it saying? Well, it's saying integrals are, in some sense, an antiderivative. That integrals and derivatives undo one another. That if you integrate a function and then differentiate it, you get the original function back. Or if you differentiate a function, if you happen to start with a differentiable function, if you differentiate a function and then integrate it, you get the original function back. Integrals and derivatives undo one another, or they are inverse operations. So I'll throw in an IE, integral dx and ddx are inverse operations. Now I'm being very lax here with this notation, right? What the hell would this even mean on its own? Just like what would this even mean on its own? We've talked about what this is. It's a differential operator. We can kind of talk about it on its own. Turns out the integral operator can be talked about on its own as well. And I'll get into details about this thing and what it means to have this without bounds down the road. But integrals and derivatives are inverses, are opposite operations. One walks you up the smoothness chain, one walks you down the smoothness chain. One walks you up the derivative chain, one walks you down the derivative chain. They undo one another. Those are the two big things I want you to remember kind of conceptually and deeply about the FTC1. So let's solve some actual problems. The sort of problems we can solve are the sort of things that ask for derivatives of stuff like this. So let's say I let capital F of x be the integral from 0 up to x of e to the negative t dt. And I say, okay, I want you to find for me capital F primed of x. Well, this is ripe for FTC1. So I would say f of x is equal to integral a up to x of little f of t dt, where a is 0. Turns out that doesn't really matter. And little f of t is e to the negative t. Right? This is the thing that we have in FTC1, and this thing that we have in this problem fits that mold. It's just that the little function inside f of t is e to the negative t. And the number down here at the bottom, a, is 0. Now you notice that this function, this thing doesn't really care about a, right? It doesn't, nowhere else in the theorem is that number referenced. It actually turns out to not be important. But this is a big deal, recognizing that the inside function is e to the negative t. So we could say thus, by FTC1, capital F primed of x should be equal to little f of x. And what is little f of x?
E to the negative t.
Almost. Be very, very careful here. You're correct about the shape of the object. F of t is e to the negative t. So f of x would be, if I swap an x in here, what do I get?
E to the negative.
E to the negative x.
Very good, yeah. Very good. That's it, you're done, right? Easy, 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 easy. All we're really doing is taking this variable and plugging it in here. If you want to differentiate something that looks like this, all right, if you got a function defined like this and you want to differentiate it, you just get this thing with this variable swapped in. Real quick here, another way to say this is d dx of integral 0 up to x of e to the negative t dt is e to the negative x. And I think this notation kind of makes it easier to say what see what I mean when I say the integral and the derivative are inverse operations, right? If you apply the derivative to the integral, you get the thing inside. It's just that you have to swap the variables. So this would be your answer, right? Really just this is your answer. And you can explain that answer either way you want, right? You can say by FTC1 it's this, or you can just say this. I like this notation. I think that this has some benefits, but the way the theorem is phrased in the textbook is just like this, right? So you recognize that your function fits the shape of FTC1, so its derivative should be the little guy inside with the variable swapped. But this kind of shows the inverse operation thing a little better, and it just looks cooler, right? Doesn't this look scary? You want to scare the shit out of someone who's just starting this class, show them this. Questions on this example? Where the pieces are coming from, what any of these things mean? Okay, let's try one more along these lines, and then I'll introduce the second fundamental theorem. Let's find capital G prime of x, where g of x is equal to the integral from, let's see, we can do that. Yeah, let's do that. Say the integral from 1 up to x of the natural log of t dt. Just to be clear, one way you could solve problems like these is to try and evaluate this integral, try and find a formula for this function, and then just differentiate it. But the two examples I've chosen here are such that evaluating this integral is tough. So you really want to use FTC1 to do this. Here again, all we have to do is identify little f. Little f of t here is natural log of t. So I would just say by FTC, I should call it maybe little g here. I'm sorry, because I'm calling this big G. I'm going to call this little g. By FTC1, big G primed of x should just be equal to little g of x, which is the natural log of x. So again, just taking this variable, plugging it into this thing. That's your derivative. There is a way to get the chain rule to interact with FTC1. If I had something up here that was more complicated, like x squared or e to the x or sine of x, there's a way to calculate those derivatives. You would still be plugging this thing in here, but then you would need to multiply by the derivative of the thing up there. I will show you a proof of that, but only after we have FTC2. It's a little easier to digest once we have more context. So last call for questions on this or the previous example. Okay, then we're going to come back into kind of explain mode here, and I'm going to show you a motivating example for FTC2. We'll see if we can't discover FTC2 the same way we discovered FTC1. So again, I'll say, consider the example. This time I just want to compute the integral from a to b of, let's say, x dx by interpreting it as an area. And note, we can assume that 0 is less than a is less than b. So I'm going to assume that a and b are both positive. That way I can draw a picture for this thing without any ambiguity. The upper bound here, the two numbers that surround the integral are called the bounds or limits of integration. This is the upper bound or upper limit. This is the lower bound or lower limit. So you remember, we always read this as the integral from a to b. And so the bottom guy is generally the smaller guy. All right. I'm going to draw the picture. And we're going to compute using geometry because we're told to interpret as areas. So this is the line y equals x. This is my x-axis. And I was told to assume that a and b are both positive and that b is bigger than a. What that means is that the integral from a to b is this area, which I will, as we've been doing, shade in pencil. All right, that's what I want. There's a handful of ways to cook up this area. We could divide this into a little rectangle and a little triangle like this. But let me show you another way to do it. Purple, and some color here. I can think of this region as being this large purple triangle. Coming all the way over here, minus this little blue triangle. So looking at it, would you agree that the pencil shaded area is the area of the big purple triangle minus the area of the little blue triangle? I certainly think it is. I take the big purple triangle and then I delete the little blue triangle. What's left is the pencil shaded area. So let's say it like that. The integral from a to b of x dx is equal to the big triangle area minus the little triangle area.
Would one ever be more accurate than the other, or are they the same accuracy?
Same accuracy. Both methods would yield the exact area in this case. Yeah, because this region is simple enough that we can always compute it exactly. So we can take this rectangle here, plus, it's hard to highlight, plus this triangle here, and that would give us the exact area. Or we could take the big purple triangle and subtract the little blue triangle. Both would be exact. So we're not estimating here. We're actually computing the exact value. And we're choosing to do it like this because it has some symmetry. It looks really nice. I mean, symmetry in terms of algebra. So let's see what we get. The big triangular area is going to be 1/2 his base times his height. So we're along the line y equals x, which means this point right here, which is at x equals b, has x coordinate b and y coordinate b, right? Because y equals x everywhere along this line. Oops. And similarly down here, this point is a comma a. So the area of the big triangle is 1/2 this base times this height. Well, what is that base? What is this length? Let's see, we have something in chat. Yeah, it's b. And what is that height? And the height right here. Also b. So this is 1/2 b squared. And I'm going to swap colors around here a little bit to help you see something. Minus. Now, what is the area of the little blue triangle? Well, same sort of formula, right? 1/2 base times height. The base of the little blue triangle is a, and the height of the little blue triangle is a. So this would be 1/2 a squared. And as I've written these things, you see I've chosen the colors there a little bit strangely. That's to emphasize something in particular. These are both 1/2 times something squared. And the somethings are the a and the b, which were the bounds for integration. This is an output from some function, and this is an output from that same function. There's actually, we see this so much that there's a special notation for this. So first, what's the function that we plugged b and a into here? If you were to imagine this and this as both coming from some function, you plug b into that function, you plug a into that function, you subtract them, what would the function be?
1/2 x squared.
Hell yes. So the notation for this is 1/2 x squared evaluated. So this bracket on the right means evaluated from a to b. You always do upper minus lower in this notation. And what do you notice about 1/2 x squared and the function that we were integrating? What's the relationship between those two things?
The antiderivative?
Hell yes. This is the antiderivative for this. So the integral from a to b of some function is equal to the antiderivative for that function with b and a plugged in and subtracted. In other words, the integral of little f is equal to capital F evaluated from a to b. And the exciting thing here is that we say, note, capital F of x equals 1/2 x squared is an antiderivative for little f of x equals x. So the two big things behind FTC 1 and 2 is this connection between the integral operator as we've defined it in the past as an area and this concept of an antiderivative. This is huge. Why is this huge? Well, what if I asked you to evaluate the integral from 0 to pi of sine x? Good fucking luck getting in there with your rectangles and getting that perfect. And this sure as shit isn't going to happen, right? Sine x is not built out of like little nice triangular regions. It's all wonky and curvy. But if you find an antiderivative, then you can just plug in the bounds and subtract them, and that will give you your integral. This is unimaginably huge. In fact, this is so important that not only is it what we're going to be doing for the rest of the semester, it's what you're going to be doing for the first like half of Calc 2. So let's go ahead and say it. FTC2. Fundamental theorem of calculus. And this, you will see me and hear me abbreviate it as FTC2 quite often, because it's a bit of a mouthful. This says, if little f of x is integrable on the interval a to b, and big F of x is any antiderivative for little f, then the integral from a to b of little f of x dx is equal to capital F of b minus capital F of a. And we have a notation for this because the way solving these problems works, you first find an antiderivative and then you plug in the bounds and subtract. So the kind of in-between step that we end up writing here before evaluating, we usually write capital F of x from a to b for f of b minus f of a. So this means this. Another way people write this sometimes is capital F of x with just a bar here from a to b. Either one is fine. I used to use this notation a lot, but I've started using this notation because the evaluation operator behaves like parentheses. You can factor and distribute and do all the things that you normally think of doing with parentheses with respect to the evaluation operator, but either one. And you'll see this in the textbook. You'll see this in the textbook. These things are just shorthand for this because the work is usually in finding an antiderivative. You're like, okay, how do I do this integral? Well, I need to find an antiderivative and then I'm going to plug in the bounds. So your first step is finding the antiderivative. You want to get that written down so you don't forget it. And then in a separate step, plug in the bounds. Some common mistakes, you always subtract upper minus lower, right? So you're going to plug in the upper bound here for x and then subtract from that what you get when you plug in the lower bound here for x. This, like I said, is a huge deal. It's not at all trivial. So let me show you some problems we can solve now that we couldn't solve before. Let's find the exact area bounded by little f of x equals sine of x from x equals 0 to x equals pi. Well, we know that that area, I can sketch sine really quickly, and I'm doing this. But all right, we know this is what the sine function looks like from 0 to pi, and come over here and continue doing its little wavy thing. The area we're after is this area. Sorry for my wavery line over here. This really shouldn't do that. It should look more like this. And you know, this is starting to do something like this. There we go, it's a little better. So this is f of x equals sine x. And you know that that area, the area we're asking for, the shaded area here, the exact area is equal to the integral from 0 to pi of sine x dx. All right, remember the exact area bounded by f of x and the x-axis between a and b is the integral, the definite integral from a to b of f of x, which is what we're looking at here. So this area is this integral. Now in the past, when you had to find an area, you would try filling up this space with rectangles, or you would try to find some way to chop this space up into like circles and triangles and rectangles. Or you would write down your Riemann sum, especially if you want an exact area, you would write down the Riemann sum for this guy, and then try to take the limit at the end as n goes to infinity. If you tried to do that for this function, the kind of summation formula you would need at the end would be impossibly challenging. It's not one you have, and it's not one I could provide for you nicely. It would be extremely hard. But now we have the tool. The tool is FTC2. So here's what we do. We need to find an antiderivative for the sine function. What is an antiderivative for sine x?
Negative cosine.
Mm-hmm. So I say this is equal to negative cos x evaluated from 0 to pi. And that's why this step is nice, right? Because in a step, you're going to find your antiderivative, but you don't want to go plugging these things in right away. You just want to record what you found. And that's why this notation is so nice. And then what is that? Well, this is, we plug in the upper bounds. This is negative cos of pi minus negative cos of 0. So I'm just taking this thing, plugging in the upper bound, and then subtracting what I get when I take this thing and plug in the lower bound. Negative cos of x with pi plugged in minus negative cos of x with 0 plugged in. This minus comes from the theorem, right? It's built into the theorem. What is the cosine of pi?
-1?
Yeah, cos of pi itself is -1. So this is -1. So Fabrice, you're correct that the whole thing there is +1. And then here I'll have minus makes plus. What is the cos of 0?
1.
+1. Good. So I have the negative of -1, which is 1, plus 1. So that area is 2, ladies and gentlemen. Isn't that neat? The sine function in here, as weird as it is, you know, it's spitting out some funky ass numbers between here and here, like, √3/2 and 1/2 and, √2/2. It's spitting out all sorts of weird things in here, and it's all curvy and shit. But the area bounded by the sine function from 0 to pi is exactly the whole number 2. That's very nice. So what is FTC2 really telling us? It's telling us we can find the area bounded by a function relatively quickly if and only if we can find an antiderivative for that function. FTC2 says that the area problem is exactly as hard as the antiderivative problem for any given function. So you want to find the area bounded by 1/x, find an antiderivative for 1/x. You want to find the area bounded by cos x, find an antiderivative for cos x. Let's try one more. Let's do the one I mentioned there. Let's talk about 1/x a little bit, because this is special. I'm just going to phrase it in terms of an integral this time, because that's how most of these problems will be given. Evaluate the integral from 1 up to e squared of 1/x dx. Fabrice asked an interesting problem in chat, question in chat that I'd like to address. How do we know when to use FTC1 versus FTC2? It depends on the problem and what it's asking. If the problem is asking you to differentiate a function that's defined as an integral, then you're going to use FTC1, right? So FTC1 is all about finding derivatives of functions that are themselves defined as integrals. FTC2 is what we use for evaluating definite integrals. So looking at this problem, I would say, okay, there's no variables in the bounds. They're not asking me to find a derivative. This thing isn't even a function. This thing here is a number. What number is it? It's the area under 1/x from x equals 1 up to x equals e squared. So if you're just straight up evaluating an integral, then you're going to use FTC2. So what does 1/x look like? It looks like this. You know, we have a vertical asymptote at 0 there. Here's 1. We'll call this e squared. So what we're looking for here is just this area. And most of the problems will be like this. Most of the problems that relate to the fundamental theorem of calculus will have you using the second fundamental theorem of calculus to just evaluate an integral. But if you had something like, you know, let capital F of x be the integral from -1 to x of blah, 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 find capital F prime, then you're using FTC1. So FTC1 will only ever use that when you're being told to differentiate some function that is defined as an integral. Everywhere else, FTC2. Okay. How do I do this? The integral from 1 up to e squared of 1 over x dx should be an antiderivative for 1 over x evaluated between bounds. So my bounds are 1 and e squared. I just need to put in here the antiderivative for 1 over x. What is an antiderivative for 1 over x?
ln of x.
Yeah, and if you remember our discussion, we want to be a little bit careful here. We want to say it's the ln of the absolute value of x. Remember, that's sort of, that's the result that we were able to get by thinking about x as being positive and negative. Because the bounds here are both positive, you could get away with just writing ln x, but it's good to get in the habit of writing ln of absolute value x, because that's the more general and true statement. And so this would be the ln of the absolute value of e squared minus the ln of the absolute value of 1 e squared and 1 are both positive numbers, so their absolute values are just themselves. So like the absolute value of 1 is just 1, the absolute value of e squared is just e squared. What is the ln of 1?
0.
Very good. What is the ln of e squared?
2.
Good, 2. So this is 2 minus 0, or just 2. And believe it or not, in a slightly more grown-up math class, this is how we define the natural log function. In real analysis, we usually define ln of x to be the integral from 1 up to x of 1 over t. So the area bounded under the 1 over t or 1 over x function between two numbers. That's usually the slightly more grown-up definition of the natural log function. You don't need to stress about this at all, but it's just a neat fact. Okay, how am I doing on time? There's one more thing I would like to share with you guys today, and we have time for precisely that. So I would like to take a look at FTC1 in the context of FTC2. Proofs of either of these are a little bit challenging, especially if you don't want to be circular with your logic. I'm not going to prove both of them, but I will use FTC2 to prove FTC1. And then we'll use that to sort of extend FTC1 into a special case involving the chain rule. Questions on this example? No, there's no plus c being written in here. Let me make a few more little comments on the definite integral before we ramble away. So some things that are useful to remember. Some of these are things I've shown you in the past, but I just want to remind you. Remember always that the integral from a to b of f of x plus or minus g of x is the integral from a to b of f of x dx plus or minus the integral from a to b of g of x dx. So if you have a problem that's tough for some reason, but is made up of multiple pieces, you can always split it apart. This means you can kind of worry about the antiderivatives separately. If you want to do some of it geometrically, but you want to do some of it using FTC2, you can do that. Just split it up. You can split up integrals over addition and subtraction. Remember always that constant multiples pop out of integrals. This can also be useful when thinking about antiderivatives. Sometimes a constant in front of a function can obscure the antiderivative a little bit, and we know that in order to evaluate this, we would need to find an antiderivative. Well, just like we said when we talked about antiderivatives, how constant multiples kind of come along for the ride, they can pop out of the definite integral, and then you can focus on just finding an antiderivative here. Other useful facts. One of them we used today, the integral from a to a of f of x dx is always 0 because the width is 0. There's no area from a to a. The region is too thin. It's infinitely thin. Another fun fact, integral a to b of f of x dx is the negative of the integral from b to a of f of x dx. So if for whatever reason your bounds are in the wrong order, you can flip them over to put the bigger guy upstairs. The process of flipping the bounds over pops out a negative. You can also use this to absorb a negative. If you have a negative out front of your integral that for whatever reason you want to suck up into the integral, flip the bounds over. Was there anything else we wanted to say here? You spoke about definite integrals. Oh yeah. Always remember that the integral from a to b of f of x dx, this is a number. If you have a particular number a and b, and you have a particular function f of x in there, then this is just equal to a number. It's the area, the signed area under f of x from, I should say, bounded by, because it's not necessarily under, it depends on whether positive or negative, from x equals a to x equals b. I say this to emphasize the middle part. This is a number. There will be another object called an indefinite integral that we will approach soon. And those are not numbers, but they look similar. They will be functions, or actually infinite families of functions. But I just want to remind you that if you have a particular function f, right, if you've got an actual function in here, and you have actual numbers for the bounds, like 0 to 5 or 1 to 7 or something, then the output of this is always a number. It's the area. So these basic rules, facts, whatever, together with FTC2 are all you really need to compute any integral. There was one more property of the definite integral that we listed last week about, if C is between A and B, integral A to B is equal to integral A to C plus integral C to B. And that's a useful fact as well, but we don't use it as much. These are the main things you'll be using as you compute integrals with FTC2. Okay. I don't think any of this should be new, but since we've talked about antiderivatives between definite integrals and now, I just wanted to remind you of these properties because they will be useful this week. What else? There are some symmetry things we can talk about, but I want to show you how the theorems interact. So let's proof of FTC1 from FTC2. So remember what FTC1 says. FTC1 says we want to show that the derivative of the function f of x equals integral a to x little f of t dt. This function has derivative capital F primed of x equals little f of x. So how do we do this? By FTC2, the integral from a to x of f of t dt would be equal to capital F of t evaluated from a to x, where capital F is any antiderivative for little f. And this is, again, just by definition of the notation, capital F of x minus capital F of a. So big F primed of x is equal to ddx of f of x. And what is f of x? That is ddx of the integral from a to x, little f of t dt. And the integral from a to x of little f of t dt, this is capital F of x minus capital F of a, because we just computed that integral using FTC2. And this would be ddx of capital F of x minus ddx of capital F of a. The derivative of this piece is 0 because a is a constant. So f of a is a constant, and the derivative of a constant is 0. On the other hand here, the derivative of capital F of x would be would be big F primed of x. Over here, this is 0, and big F primed is little f. Right? Because big F is an antiderivative. So the derivative of big F is little f. In other words, the derivative of the integral is the thing inside. So that's your proof of FTC1 from FTC2. Where this gets fun is if we try to generalize a little bit more. So let's see how this interacts with the chain rule. And this will be the last thing for today. So the chain rule with FTC1. Suppose we want to differentiate the function capital F of x equals integral from a up to some other function of x, little f of t dt. right? So all of our FTC1 problems have big F being defined as the integral from a up to x. But what if instead of an x up there, you have some more complicated function u of x? Well, by FTC2, if we find an antiderivative, big F for little f, then integral from a up to u of x of little f of t dt is going to be big F of u of x minus big F of a. So the derivative would be equal to, and this is, I should say again, this is big F of x here. The derivative here would be d dx of the integral from a to u of x, little f of t dt, which is d dx of big F of u of x minus big F of a. And again, the f of a piece is going to differentiate to 0 because it's a constant. The trick is that down here, you need to apply the chain rule. So this is going to give you big F primed of u of x times u primed of x. I'll show you how we use this, but this is something you should remember. Specifically, if you're trying to apply FTC1 to a function like this, you do have to plug this in here, just like you do if it's an x. This thing, whatever's up here, goes in here. But then you also have to multiply by the derivative of the little function up there. So let me show you an example. Find the derivative of big F of x equals integral from 0 to x squared of, what do we want to do here? Let's do something fun. How about the inverse tangent of t dt? I want to point out that we don't know an antiderivative for the inverse tangent of t. We know its derivative is 1 over 1 plus t squared, but we don't know its antiderivative. And finding an antiderivative for this function is actually a little bit hard. We won't learn how to do it in this class. I'll teach you in Calc 2. But by FTC1, big F primed of x should be what I get when I plug this in here. But then by the chain rule, as shown above, we need to multiply by the derivative of x squared, which is 2x. So this would be the inverse tangent of x squared times 2x. Or most people would write it as 2x inverse tangent of x squared. This is how the chain rule interacts with FTC1. I'll show you one more example in the alternate notation, and then I'm going to let, oh no, we're out of time. All right, I'm going to go ahead and end here then. We can look at one more example of this sort of thing on Wednesday, but those are the two fundamental theorems of calculus, lads and ladies. This is the good stuff. So you are now saved from capital sigma summation notation. You don't need to use that anymore to evaluate your integrals. You now have the fundamental theorems of calculus, which will give you a means of evaluating integrals by taking an antiderivative and then plugging in the bounds. That is a big, big step So be on the lookout. A new homework will drop today. I'll need a little bit of time to polish it up, see where my other class lands, and then I'll put together the homework set based on that. The FTC1 problems are somewhat interesting problems, but they're nowhere near as important as the FTC2 problems. So I will put a few FTC1 problems on there, probably just one or two that require this chain rule thing. But then the rest of the homework for the week will be FTC2 stuff. So that is what you want to be practicing. I encourage you to read the textbook. We are in section 5.3 now, which is on the fundamental theorem of calculus. There's really two of them, of course. And they go through a similar sort of discovery process that we did, where you realize that this thing is an antiderivative. The proofs are in there. They're not that bad. If you want to go through them, they're digestible, but it does involve a meaningful amount of work with inequalities. So we're not going to prove those in this class, but we do need to get to a place where we can use these things. So take a look at the textbook. It has more examples. I invite you to look at all of them, and then get a look at the homework. The homework is good stuff. And that's where I'll leave you guys for today. If you want to talk about anything else, you can come see me in office hours or send me a Canvas message. Remember, I'll be applying the curve to your exams today. I apologize I didn't get to that last Friday, but it's going to happen today. If there's anything else you need to talk about, just come see me in office hours. Take care, guys.